Swayam Prabha. Digital India. Educated India.
Now, let me also tell you a few other things related to this. I remember I mentioned, so we wrote out the LP for, we wrote out the LP duality theorem assuming this particular form for the primal LP, that we took it as standard form, because every problem can be reduced to this sort of standard form, and then you get its you can, and this was the dual of that particular of the standard form LP. Now, if you have a LP which is not in standard form, okay, if you have LP not in standard form, So, for example, say suppose you have a LP that looks like this. Say suppose you have a LP that is say suppose this is your LP. Now, what is the dual of this one? It turns out, so the way to get to the dual, so this LP would, this primal will also have a dual. Okay. Now, its dual will not take the same form as the standard form dual. Its dual will take a different form, but the way to get there is that you can convert this to standard form. Then do a dual of standard form, and usually after this some manipulations are needed. Okay, because usually this will lead to some redundant variables which you can eliminate easily and so on. Do a few manipulations if possible, and then that would give you the dual of, that will give you a dual problem. Now, what is the dual of this one? It turns out it is maximizing B transpose Y, A transpose Y less than equal to C, and Y greater than equal to 0. This is the form of the dual of this particular LP. You can as I said, consider many other different linear programs and find their standard find their duals by just converting them to this by converting them to standard form and then manipulations and so on. Yes. This is the same A as this A, the B is the same as this B, C is the same as this C. Yes, some variables will get dropped. Yes, it is possible that some variables will get dropped. No, so it will come. You can bring it down to this form. So this is also another sort of settle point. See, an optimization problem can have many different forms that are all giving the same optimal value. Remember, at the end of the day, the duality theorem only pertains to the value of the optimization problem. That you can always introduce additional variables, manipulate, remove variables, etc., while not changing the optimal value, right. So there is no fixed form for an optimization problem. That is a matter of, but all we know is that yes, this is a form for the dual. All right. So this is how you can, if you have a LP in that is not in standard form, then you can this is the route by which you can get its dual. All right. Okay. So as the last topic on linear programming, let me mention to you one other thing, which is another type of problem which comes up, which can be written as a linear program. and that problem is the problem of shortest path. So, the problem that I wrote here in this the network problem here was that you had an old phone and you had a new phone, you want to transfer data from an old phone to the new phone, but then the links that over which the data could flow had limitations of capacity, right. So, you could not push data beyond a certain MB per second along these links, right. So, there is a different type of problem which is of the following kind, that you have a source node, you have a destination node, okay, say the source node is say Mumbai and the destination node is say suppose Delhi. You can go from this source node to this destination node over many different possible paths. One way is that you can go till you can fly till somewhere here, then you can go by then take another flight and get to Delhi. Another way is that you can go from S to some other intermediate node, then you fly till here, or you then fly directly to Delhi from here. Another possibility is you can go from here to here and then go there to here, etcetera, etcetera, etcetera. So, that you can see there are numerous possible ways by which you can go from one node, from the source node to the destination node. Okay. So, now if you have this kind of if you have a general network like this, the problem which we are asked what we want to ask here is what is the shortest path. So, every link here suppose has a length, okay, the length or a length or a cost associated with it. Okay. So, the length say for every I and j, okay, every I and j has a cost C I j, and these are all directed edges. There is a cost to go from I to j, cost C I j to from I to j. And what we want to know is what is the route from S to T of minimum cost. What is the route from S to T of minimum cost? Now, this is a problem that we end up solving every day when we use Google Maps to find a route from point A to point B. This is exactly what Google Maps is ending up solving for you. It's assuming the cost as say the travel time from I to J. Now, if you are if you are within the city, maybe travel time is all you care about. In another, when you are traveling from from intercity, you are caring also about say tolls. Maybe if you are driving on toll roads, or your cost of a ticket if you are changing modes of transport in between, etcetera, etcetera. Okay. So, you can define cost in whichever way you like. So long as you have one consistent notion of cost, this problem can be posed in this particular way. Okay. Now, we want to know what is the shortest in the sense of the total cost that you would incur of a route from S to T. Okay. So, the cost of a route from S to T is simply the S to T is sum of C I j, where I comma j is in the I comma So, whenever I comma j is an edge that you use in the root, it costs you C I j, okay, and the cost of the entire root is the sum of all these C I j's that are where I comma j lies in the root. This is the cost of traveling from I to j. Now, here you can see how intuitively how would you solve a problem like this. See, if you want to go from Mumbai to Delhi, you can see already this simple little graph is an extremely complicated graph. Right? How would you solve a problem like this? You would say, well, let me try out this route, one route here. I go from my the source node to one node, then I try out from here, let me try out this particular possibility, let me try out that particular possibility, etc., etc. You basically have to enumerate a huge number of possibilities and to try to get to the shortest path. Now, that seems like an extremely complicated optimization over so many, because even just enumerating all the possible paths itself is would take you a lot of time, right, and then listing them all out, just simply enumerating all the paths and then trying to find which is the one that is of least cost. Now, it turns out this can be solved using linear programming in a very elegant manner. Okay, so, let me explain how that is done. Okay, so, on the roots here, now I have, say, if I have a node I and a node j here, I have a cost C I j written for that particular link there. Okay. Now, I want you to, before I write out the linear program, I want you to appreciate the difference between this problem, which is the shortest path problem, and the problem of maximum flow. The problem of shortest path is simply says I want the shortest path to go from S to T without, but when I travel on any edge in the path, any edge or any link I j on the path, it costs me something. There is a certain toll or a certain fee that I have to pay, but the capacity is virtually infinite. Any amount of flow can go on. Okay. So, the problem, whereas the other problem, there is no cost associated with traveling from I to j, but there is a limitation of capacity where you cannot send more than a certain amount of flow. So, you can think of capacity and cost as two different things. Capacity is how many cars, say, a road can take, capacity of that road. So, the cost of traveling on that road is the toll you have to pay for traveling on it. These are two very different things. There are finitely many nodes. Yes, there are finitely many nodes that by which you can, and we want to know the shortest path on that particular from the source to a destination node. No. So, even in a real life problem, you need to model it in such a way that it brings it. You have finitely many nodes and finitely many decisions to make. Okay. So, even though there are just finitely many, the number is too large. If you just think of all the possible routes you can take, the number of combinations you can make is immense, right. So, yeah, but what's very nice is you can actually solve this using linear programming in a very clean way. Okay. So, as I was saying, these are two different problems. First problem is that of the earlier problem, which is the maximum flow problem, is about sending the maximum flow over capacity constrained networks. Okay, that is about finding the bottleneck. This problem is there is no bottleneck. You can set as much flow as you like, right? But which links will you choose is the question, because the links that you will choose based on the links you will choose, you will incur a cost. Okay. So, now, since the cost here will what we will do is say, let us say, okay, let me write this in this sort of way. Now, just imagine, suppose I had 1 unit of flow entering S, just 1 unit, okay, some 1 unit of goods, say 1 truck or whatever, 1 unit of goods, not 1 truck, 1 unit of goods entering node S, and which has to reach node T. Okay. So, it enters enters here and leaves and has to reach T. Whenever this flow, one unit of flow reaches any particular node, say it reaches this node I, it has a decision to, there is a decision we need to make, which is that out of all the links that are going out from node I, which one should I pick? Now, suppose at node I have these links which have costs say 10, 20 and 30. These are the costs of the links, not capacities, costs of the links, which okay. And suppose from, I know that from here, let us say for simplicity, from here this is the cost that I would incur, say if I came here, and then from here if I had to go all the way till Delhi, here is suppose the cost I would incur. Someone told me this number, that here is the cost I would incur if I came here. So, if I came to node I and I chose this particular link, it would cost me 20 to get to Delhi. If I chose this particular link, it would cost me 10 to get to Delhi, the other one would cost me 30 to get to Delhi. Okay. Not just to the next node, I am taking suppose all the way till Delhi, okay, for simplicity. In that case, where would you send your flow? You would send the flow onto the one that has the least possible least cost of all of these, right. Naturally, the reason is because the links do not have any capacity constraint. There is no reason for you, when the flow arrives at a particular node, there is no reason for you to split the flow across multiple edges. You will always pick the one that has the least possible cost to reach the destination from there onwards, isn't it? So, this simple observation is all that we actually need here. Okay. So, let us write out some variables, and I will explain to you how this works out. Okay. So, suppose x I j. So, suppose I am sending. So, imagine flow 1 into node S. Okay. So, you send a unit flow into node S, let x I j be the flow on link I j. Okay. X I j be the flow on link I j. So, what is the objective expressed in terms of x I j? Suppose I had if I have, so if I am sending flow x I j on link I j, okay, what we will use this interpretation, and it will later turn out that this is actually correct. So, we will have this interpretation that this is equal to 0 if I comma j is not on the chosen path and 1 otherwise. So, it will turn out that if it is not on the shortest path, then x I j will be 0, which means that it will not send any flow on that. And if it is on the shortest path, it will have to send the full flow on it. So, the reason for that is exactly what I just said. See, whenever the flow arrives at a particular node, if you look at the cost that it has to incur to get to the final destination, and the path that will give you the least possible cost, the entire flow will go on to that path. It has to be. So, if at all a flow is there on a path, that path must be the one that encounters the least cost. It cannot be that part of it is there here, part of it is there, part of it is there on another part, right. So, now let x I j be the flow on link I j, and it will have we will take this interpretation that it will be 0 if I j is on the is not on the chosen path and 1 otherwise. So, the objective is to simply then in these terms is to minimize this. So, what is this? This is the total cost of a chosen path. And now all I need to make sure is that these flows satisfy my flow conservation constraint. So, I look at x j. So, my flow conservation constraints again my inflow is sum over j such that I j belongs to E. This is the inflow into I. Then I have a sum over j sorry I and this is not I j, this should be j I belongs to E. This is I j belongs to E. This is this should be equal, this is 1 if I is the source node, 0 if I is neither the source node nor the destination node, and minus 1 if I is the destination. Is this correct? Sorry, my mistake here. Sorry, this should be the other way around. This should be minus 1 here. Yeah, that's correct. So, this should be minus 1 if I is the source node, because so that's positive 1 inflow into I. So, that's correct. So, it's minus 1. This would be, it would be 0 at all nodes except for the source node and destination node, and it would be equal to 1 at the outflow node, and we have that x I j is greater than equal to 0. So, what have we done? We have taken the problem of shortest path and of which was about trying to enumerate all the possible paths in the network and trying to find the shortest path, and we have converted it into a problem of minimizing the cost of flow. He said, let us imagine a unit flow that was sent in. If a unit flow was sent in and it had to follow my flow conservation equations, right, what would be the path it would choose? It is almost like, you are sending a flow of water and it is trying to find the path of least resistance or least to go from a particular source to a destination, right. You solve this and it turns out that this actually gives you the shortest path. Okay, so, this is a linear programming formulation of a problem that on the face of it looks extremely complicated. Just if you had to enumerate all the possible paths would be a horrendously complicated problem, but knowing but with this sort of way of looking at it, we are able to reduce it to a linear programming formula. Okay. There are many other such problems that end up getting reduced to reduced to linear programming. That is why linear programming is such an extremely powerful tool across all of engineering and science. Okay. All right. So, with this we conclude our study of linear programming. What I have not touched upon at all is algorithms for linear programming, because I plan to come to that next. But what I want you to remember, the biggest takeaway I want you to remember from linear programming is linear programming duality and associated Farkash lemma. Okay. So, Farkash lemma is something that we will use again, and in one shot you will see how that gives us also optimality conditions for any type of convex optimization problem. Okay. So, that would be next on the agenda. Right. Okay. Okay. The form of there is another form of, let me mention this also. So, there is another form of Farkash lemma which we will different form, which will be very useful in the next lecture. So, it says, so let A in R m cross n and C belong to R n. Then the following statements are equivalent. For all x such that A x is less than equal to 0, we have C transpose x less than equal to 0. C. For all x such that A x is less than equal to 0, we have C transpose x less than equal to 0. Okay. And then there exists a lambda greater than equal to the other statement. So, the Farkas lemma is saying that there are two statements that are equivalent. The first statement is that for all x such that A x is less than equal to 0, we must have C transpose x less than equal to 0. The second statement is that there exists a lambda greater than equal to 0. So, lambda is in R m, lambda greater than equal to 0, such that A transpose lambda equals C. So, this statement is essentially this version of Farkas lemma. It's a different form of stating Farkas lemma. This is not stating it in the form of two statements out of which only one can be true. Rather, it is saying that these two are equivalent. These are two equivalent ways of saying the same thing. One is that for all x such that A x is less than equal to 0, we have C transpose x less than equal to 0. The other is saying that there always is a lambda greater than equal to 0, such that A transpose lambda is equal to C. Right. So, what this basically is, if you look at the second statement, what it is saying is that it says is that C is in the cone generated by the columns of A transpose. C is is present in the cone generated by the columns of A transpose. So, you can always find a conic combination of the columns of A transpose such that that conic combination equals C. Right. The first statement says something completely different. It says that A x is, whenever A x is less than equal to 0, it has to be that C transpose x is also less than equal to 0. Okay. So, columns of A transpose is consider a cone formed by the columns of A transpose that contains C. That is one statement. The other statement says that if you look at the vectors x such that A x is less than equal to 0, then they must make an obtuse or greater than equal to 90-degree angle with C. C transpose x less than equal to 0. Now, it turns out these two are actually equivalent. Okay, so, this is another form of Farkas lemma, and we will this again can be proved using linear programming duality. Again, you have to think of the right sort of linear program, look at its dual, and again you will be able to argue it from there. In fact, you may even be able to prove linear programming duality itself from this particular Farkas lemma. So, without going through separating hyperplanes and so on. So, a first principles proof of this Farkas lemma would be as hard as LP duality itself. Okay. All right. So, important thing, the reason I mention is now is that remember this, we will use this in a definitive way in the next class. Okay. So, we will end it.